Good morning, everyone. This is Team IOTC, the sixth presenter of today's presentation. Our team's design project was to participate in 18th Robot Aircraft Tournament. For this, we developed our own hardware and software very hard for more than 6 months to test the limit of our knowledge. Order of our presentation will go on like this as shown. The first part is the introduction. After that, we will explain what we did to realize our system. Lastly, we will show the result and the things we learned through this project. The first part of the presentation is the introduction. Our project was to participate in an 18th Robot Aircraft Tournament. Just participating in this tournament was not enough since we do it as a general design project. So we decided to fly our drone using self-developed FC and GCS. As a result, our objective can be shortened in just 2 sentences as shown. The mission is to deliver medikit to remote place. The mission profile like this. First, the drone takes off up to 30 meters high. Then it starts to go to waypoint 1, avoiding non-flight zone. Next, it descends to waypoint 2 of 10 meters high and it deploys winch more than 2 meters high. And then avoiding non-flight zone, the drone lands on place it departed. Important point of this mission that all the process must be done automatically.
The next part is about the project process. We first used PPID for the control and we could find appropriate values to make our system stable. But we thought it was not enough and added additional I factor on the RO loop. It is more complex to control altitude. At first, we tried to use only barometer for control, but using only air pressure for altitude control made the system react so slowly. So we added 2 additional PID loops using velocity and acceleration data. For point-to-point maneuver, GPS is not precise enough and slow for real-time tracking, so we used Kalman filter to estimate drone's location and control its maneuver. We integrate sensors to get appropriate data. For roll and pitch, we used complementary filter. We could get small errors like shown. We also applied EPA. But no, those sensors were used. When using meganeurometer, we had to compensate soft and hard ion distortion by calibrating it. We used IMU for calculating DCM. By DCM, you could change coordinate system of measurements. About altitude control, we used 3 sensors. Considering characteristics of each sensor, we used barometer and LiDAR as a primary sensor, and GPS as an alternate sensor. LiDAR showed the most precise result, but we couldn't use it on higher altitude due to its short range. Lastly, we used IMU and GPS on point-to-point maneuver. The major reason why we need IMU for position holding is because GPS is too slow in refresh rate. We used Kalman filter for it.
During the development, we faced an urgent need of test equipment. In limited conditions, it was too dangerous to test our FC by just flying a big drone. So we made various test equipment. With those testers, we made small drone to really fly our system outdoors. We faced many crashes due to unexpected problems of our FC. However, since the little one was designed to be broken during the test and was very easy to be repaired, this really helps reducing risks of delay. We call our drone Stork. Stork is a 680mm class quad-rotor drone with carbon frame. Its overall configuration is just like an image. We placed the FC to make sensor coordinate system very close to body coordinate system. We extended LiDAR arm out of body to reduce interference by its leg. We made a block diagram of control system based on PBS technique. You can see the overall connections between components of the drone. Main controller board communicates with external systems via radio and Bluetooth. At the same time, it controls sensors using various protocols. By giving appropriate PWM values to each motor, our drone can fly. This is a power system diagram. You can see how powers are distributed from sources in this system.
Through a series of tests, we could make our drone stable enough to do the mission. These videos are our drone during the final test. You can see scenes of our drone performing maneuver required for the flight. I will wait for a moment. We also developed our own GCS. WPF helped us distinguish UI elements from background codes. For language, we use C# for easiness of access to free map APIs. Our GCS can do what other conventional GCS can do. Furthermore, we added more functions to make drones testing much easier. Important point is that made this all by our own. This image is an overall layout of our IUTC GCS. You can see the button, layouts, and functions. Another task for this project was to design reliable but light winch. We conclude that descending winch module itself will help reducing overall weight. So we made a winch by 3D printer. The advantage of this winch is that it works on full active mechanism and very light. Unlike other winches, we introduced ultrasonic sensor to detect distance between ground, so that winch can detect cargo on its own decision.
The last part of the presentation is about results and things we learned through this project. Due to COVID-19, the tournament was cancelled. Instead, there was an evaluation flight. Purpose of it was to check whether the budget was properly used or not. We failed to achieve the first objective. We couldn't be in top 2 team in grading. The strong reason we guessed was because our system's full automatic flight was not finished. During the development, many obstacles led to critical delay in implementing full automatic flights. We could not perform automatic flight in front of evaluators, although we had extra 2 months of time. What we learned from this is that on every project, we must set an extra time for testing in schedule. If we don't, there will be significant delays if there is an unexpected problem. Moreover, we need more studies. We learned many things about control system and RTOS, but we need more. We did our best, sacrificing our times and effort than any other. Although we couldn't achieve some goal, we still believed that experiences from this project will help us broadening our understanding about control system design. Thank you for listening.